In an era of starships, drones, and self-driving cars, the demand for real-time image processing is at an all-time high. A lot of the current focus within the field of image processing has been object detection and classification, but equally important to detecting objects is being able to estimate their distance. Currently, a lot of autonomous vehicles are using LiDAR, radar, and other waveform technologies to estimate distance, but these technologies are usually very costly. For my paper, I focus on implementing a real-time algorithm for estimating depth using only stereo images in a famous image processing tool called patch match. So stereo image depth estimation is actually one of the ways that we as humans perceive distance. As an experiment, try shutting one eye and then the other. You'll notice that objects in your field of view jump from left to right. This movement, or disparity, can help us and stereo cameras perceive distance. So when trying to apply this theory to stereo cameras, there are a lot of open questions about how to accurately match pixels and objects between images. One of the most rudimentary forms of estimating distance is to use basic block matching. Blocks of pixels, such as the 3x3 block shown on the right image, are compared to similar blocks in the left image. Some cost function, usually a sum of squared errors, is used to identify the nearest neighboring block. The advantages of this method are that it's quick and uses little memory besides the images themselves. However, by just matching blocks of pixels, the algorithm cannot take into account the context of each pixel within the global scope, resulting in discontinuous estimations across what are obviously continuous surfaces. Switching gears, patch match is a famous algorithm that was introduced in 2006 by a team at Princeton in order to find approximate near-neighbor patches between two images or within a given image. This was very important for image editing tools that utilize these features in order to resize images, fill patches, and much more. The algorithm works in three phases, the latter of two repeated in as many iterations as desired. The first step is the initialization phase. This is where every patch in the first image is given a random offset or an intelligent offset based on previous information. Then, in the propagation phase, good offset guesses are shared with neighboring pixels. Lastly, in the random search phase, more guesses for each patch are made with a decreasing radius around the current offset in an attempt to escape local minima. This method is much quicker than checking each possible offset for all the patches, as most patches converge within the first one or two iterations using patch match. Deep Pruner, an algorithm published this year from the University of Toronto, explores the idea of utilizing the patch match algorithm within the context of stereo depth estimation as a method of pruning the search space of possible disparities for a given pixel. Within Deep Pruner, patch match is just one step for pruning. But from the diagram, you can see that the model first starts with a downsampling and feature extraction layer and ends with a more robust 3D cost aggregation from the depth estimations produced by patch match that also go through a refinement phase to produce a polished disparity map estimation. For my implementation, I focused on just implementing the pruning phase using the patch match algorithm. To do this, I used three different models. One rudimentary or classic model that just performed basic block matching, my algorithm that focused on the original non-differentiable patch match algorithm, and Deep Pruner's differentiable patch match that I adapted from their source code. One thing to note is that Deep Pruner's differentiable patch match chose to remove the random search phase in order to decrease their runtime, which I'll discuss a little bit more later on. To compare the three models I created, I used 6 sample stereo pairs from a benchmark dataset called SceneFlow. I ran both of the patch match algorithms using 1, 2, and 5 iterations. The runtime results can be seen in the table at the bottom, and an example of one of the output disparity mappings can be seen on the right. As you can see, my algorithm ran a bit slower than Deep Pruner's differentiable patch match, but much quicker than the basic block matching algorithm. Also, my algorithm performs significantly better in terms of error rate than differentiable patch match. I believe a lot of the errors in differentiable patch match that aren't seen in the other two models can be explained by the elimination of the random search phase. These clumps of pixels likely found local minimum at the initialization phase and propagated these findings to neighboring pixels without the chance to improve. Some of the other errors seen in all three of the models, such as the front face of the block on the left, can be explained by the algorithm's lack of global context. Smooth features such as this block make it difficult for small patches to discriminate between one patch versus another. Independent of a more sophisticated model, basic block matching does a poor job of accurately predicting depth between a set of stereo images. That being said, patch match can be used to significantly reduce the search field for possible disparities and to quickly converge at approximate near-neighbor patches. Also, more research should be done into the pros and cons of removing the random search phase from the patch match algorithm in the context of Deep Pruner and other stereo depth estimating tools.